We can also take a look at ions and classify them as aromatic, anti-aromatic, or non-aromatic. So for example, start off here with this cyclopentadiene. And so the first thing we say about this is that it's non-aromatic. And the reason it's non-aromatic is because it doesn't have this continuous p orbital overlap, right? This carbon up here is sp3 hybridized, and so it doesn't have this continuous ring. However, what if we took one of the hydrogens here, added a base, and then deprotonated this compound in an acid-base reaction? What we would get here is an anion, and now this anion can resonate with this ring. And so now we can see we do have this continuous p orbital overlap. And so now we can classify it as aromatic or non-aromatic. And so in this case, it has 6 pi electrons, right? 2 from this pi bond, 2 from this pi bond, and then 2 from this lone orbital. And so this is aromatic. And so you can see when you add a base to this compound, it becomes aromatic. And so this compound really wants to get rid of this H. And so this compound is, the cyclopentadiene, is much more acidic than you may guess. In fact, its pKa is approximately 16, so it's close to water, which is quite acidic for a hydrocarbon, right? Hydrocarbons generally are not acidic, but because when you deprotonate this compound, it becomes aromatic, it's actually much more acidic than you would think. We can take another good example of this cyclopentadiene. This time we're going to put an iodine here, and we're going to add some weak nucleophile. That way we can undergo some SN1 reaction. And if you think about the first step of an SN1 reaction, our leaving group is going to leave, and we'll form a cation here. And so again, here we have our cyclic p orbitals, and if we count the electrons now, we'll get 4 pi electrons, or 2 pairs. This means that it's anti-aromatic, right? And so this compound is highly unstable, and so this iodine really doesn't want to leave, and so this SN1 reaction is not going to happen. Even though you form this conjugated cation, it's going to be very unstable due to the anti-aromaticity, and so this reaction is essentially not going to happen whatsoever. And you can think about the inverse as well for this kind of stuff. So in this case, we have our cycloheptane, right? It's kind of hard to draw. If we have a hydrogen here and we try to come in with a base, think about the structure that it would form. Right, is that going to happen or is that not going to happen? Well, if we count the pi electrons, we get 8. And so this is anti-aromatic. And so basically this reaction is not going to happen. And so this hydrogen is very not acidic. You're going to need a very strong base to deprotonate this hydrogen. And then the inverse for this as well, right? We did the iodine example. Let's see what happens when we add an iodine here. Now we end up with a carbocation. We have our cyclic system of our p orbitals, and then here we have 6 pi electrons. And so this is going to be aromatic. And so this compound will undergo SN1 very fast, right? Because it forms this aromatic intermediate.